Hello, my name is Robert Coleman. I am the North American Sales Manager for Bowman Analytics. I would like to thank you for the opportunity to talk with you today about XRF and the equipment attributes that are essential to providing superior results. Today's discussion will cover the following topics. What are X-rays? What applications and markets are there for XRF? I'll go through a red apple's XRF illustration. We'll discuss the features for better analysis, specifically emission and detection. What is the most important objective of XRF? And what should an XRF have? What are X-rays? Let's look at the following electromagnetic spectrum so you have an appreciation for where they are in comparison to other wavelengths. X-rays are a type of radiation called electromagnetic waves. They are invisible light that have a wavelength ranging from 0.03 to 3 nanometers. The shorter the wavelength, the more powerful. So in general, the energy is higher. And just so you know, the human eye cannot detect X-ray. Most people think about X-ray imaging when they go to visit the dentist or at the doctor's office, but we use a different detector. We are not looking at density, we are looking at fluorescence. What does that mean? By bombarding the sample with X-rays, as shown above in the photo, the sample becomes excited. And that means all of the elements want to go back to a stable condition. And during this process, they emit characteristic photons. What do I mean by that? There's different energies for different elements. And these characteristics are well known and can be used to identify the element and thickness. Where would you use XRF? As you can see, there are many applications requiring the use of XRF, ranging from printed circuit board to general metal finishing to jewelry and electronics, and a whole host of industries where it's critical to know the exact composition and thickness of the deposited metals. To make this easy to understand, I've decided to use a graphical representation of red apples. If we go back to the electromagnetic spectrum, as you can see, visible light has a wavelength in micrometers. A good example here would be your ability to see all the colors in a rainbow. I thought it would be easier to use this visible light to illustrate the XRF technique and the key features that are important aspects of the spectrum analysis. In this situation, we're going to use visual light will be the XRF, and the number of red apples will be the gold thickness on a copper alloy. If your eyes were the X-ray detectors, you can see the different fruits and colors. The different colors representing different wavelengths or energy. Comparing this illustration to a plated deposit, imagine the different elements you could see, like the gold, copper, zinc, and tin in the deposit shown in the right picture. So what different features are required to see the different shapes and colors? First is emission. You have to have a source. In this case, it's the sun. In XRF, it's going to be the X-ray tube. If you don't have a light source, this is what you would see. If there's not enough light from the sun or from the X-ray tube, your visibility will be poor. Now you can control the intensity of this light source. If it was a dim light, you can begin to see the fruit, but it's still not enough emission. When the light source is brighter, or you are closer to the light source by optimizing the distance to the light source, the result is excellent clarity to allow you to see all the different shapes and colors. In summary, with regards to emission, the ideal situation is when you have a bright light source that is close to your sample. Detection. What is detection? Using the same analogy, a detector would be your eyes and brain. Without a detector, you would not be able to identify the different fruits and colors. Resolution. Let's use the evolution of a TV as a good example of color resolution and how it has evolved. When we first started out, we had analog TV that was in black and white with very poor resolution. Today, we use high-resolution digital technology that produces ultra-high definition TV. As resolution has improved, images have become clearer and easier to detect. When using a digital detector with clarity and special resolution, it allows you to separate the similar colors and shapes in the basket of fruit. In the scenario shown above, you can detect the apples from any other fruit that is similar in size or color to an apple. In effect, good resolution allows you to tell the difference in color and shape so you can separate the green apple from the red apple. Noise. Another factor to take into consideration when optimizing the detector is noise. Noise is related to the detection limit. As noise increases, detection limits decrease. Background noise prevents detection of low concentrations. It impedes the ability to clearly see all of the fruit. Distance. We talked earlier about the advantage of having the light source close to the sample. The distance of the detector to the source is also critical. As with the light source, the closer the detector is to the source, the better. Using the above analogy, visualize a Bowman shooting at a target. If the Bowman is the detector, he has a better chance of hitting the target if he is closer to the target. On the contrary, as shown above, if the Bowman is farther away from the target, it makes it more difficult to hit the target. Summarizing the important attributes of the detector, you want a digital detector that has sharper resolution with less noise and interference and as close to the target as possible. This is critical to have in the state-of-the-art XRF machine. I talked a lot about the features you want, but which one is the most important? The answer, all of them. Having a bright light source and detector that is close to the target, that has the best resolution and less noise, will provide the ideal conditions that are required for the best precision, also known as repeatability. Let's look at the following image to identify each of these critical parts. In the images, you can see all of the key components that you must have. There's the X-ray tube, which provides the light source. There's a collimator that controls the size of that X-ray beam. The filter controls the brightness of this source. And the detector allows you to see the different energy levels better with minimal interference. And the camera allows you to align your image with the detector and record the image. All of the features that we discussed, emission and better resolution through close coupling, that is, the distance between the sample and the X-ray tube, provides the best configuration to achieve the best precision. Here is a good example showing why having the X-ray source closer is better. As you can see in the image on the left, there is deflection coming out of the collimator. This deflection increases with distance. The closer you are, as shown in the circle, the more intense the signal, thus allowing you to capture more counts per second, also known as CPS. The higher the CPS, the more data you collected from your sample will increase the accuracy of your analysis. Here is a good example comparing the different types of detectors. Remember the slide on resolution as it relates to the evolution of the TV? Think of the black peak as the black and white TV. As you can see, the wavelength of this black peak does not allow you to separate the chrome iron, and nickel peaks. When you look at the blue line, as represented by a silicon pin detector, this is the equivalent to the HD TV, and you can begin to separate the individual peaks. However, it's not until you evolve to the ultra-high def TV, in this case, the red peak, also known as SDD or silicon drift detection, can you completely separate each element, different fruits, from one another. Is good precision all you need? What is the difference between precision and accuracy? If you look in the lower right image, it shows what inaccurate and imprecise looks like. As you can tell, you're all over the place. The lower left image is more accurate, but still imprecise. Grouping has improved, but not enough. Looking at the top right image, it shows a very precise target. However, it's not accurate. It is not until you are precise and accurate do you have a tight grouping hitting the bullseye every time. If you package an X-ray system with all of these key elements of emission and detection, you will have the most precise and accurate XRF on the market. I wanted to mention the importance of reference standards. In order to achieve traceable, accurate analysis, you require reference standards to calibrate the instrument. In keeping with our Bowman analogy, this is the equivalent of needing to calibrate the scope or reticle on your bow. You can use the same fruit illustration of charting quantity and size of the calibrations, or in our analogy, apples, in order to plot your regression curve to allow you to identify the number and size of the apples. As I use different sizes and quantities of apples, I can plot my results needed to identify the size and color of an unknown apple. So if you go through the calibration routine, you can make inaccurate and precise to become accurate and precise. The ultimate goal of XRF equipment is to produce highly precise and accurate results. In summary, using a system configured to have a close-coupled digital detector with proper lighting, you can achieve precision and accuracy at the highest levels.